Hello, welcome to the second video on revision in M1 mechanics for this set. And this question says that there is a particle P that moves with a constant acceleration of that much meters per second squared. Constant acceleration being the key thing there. We can only answer questions with constant acceleration in the mathematics that we're learning at A-levels anyway. But it's good to realize that that's being given and that's significant. Then at time t seconds later, t as a variable obviously, its velocity is v meters per second, so v being a vector which changes with time, and they tell us that when the time is 0, the velocity is this much. So in other words, this is kind of the equivalent of u, the initial velocity in the Suvat equations, right? U would be the initial velocity, and then this that would change, the vector v would change with time, and you could use that idea to find what the v is going to be in the future if you combine it with the acceleration, right? And we had a lesson recently where I spoke about this, but the general formula for the velocity is always at any point the vector will be the initial velocity u, in this case it's going to be this much, plus the acceleration vector times the time that has gone by. So here they're giving us a bunch of information we can put into here as vectors, and we can use that to find v. But if this question is a little bit more twisted and it doesn't say just find v, it's saying something else. It says find the value of t when p is moving parallel to vector I. Okay, so a couple of things to notice here. First of all, we need to know how to build this equation, and this one should be easy because it's just v is equal to u plus at, and you know it from normal Suvat equations, and it's also very intuitive, right? Your initial velocity plus your acceleration times the time is going to give you your final velocity, so that should be fine. The other one that sometimes people forget, but it's just as valid as this one, the vector of displacement is equal to the initial position with respect to the origin plus then the velocity vector times the time. So instead of the initial velocity plus acceleration times time, this would be initial displacement plus the velocity times the time. And that should be as intuitive as the other one, because if you start from a fixed point away at some location s0, then your new location after you've been moving with a velocity v for a certain amount of time t, velocity times time is distance, so that will take you to the new location, and so this new vector, which you can call the general s from the origin, which is this guy, will be given by s0 plus this vector vt. That should hopefully make sense. So let's use this equation to find what's going on, or at least to write down everything we know and see if we can figure out what t is when that condition they're giving us is satisfied. What's the condition? P is moving parallel to vector I, and moving vector is this guy, is the velocity vector. So what they're telling us when they say that the P is moving parallel to vector I, it means that at some point that vector, that particle is going to be moving in this direction, because that is I. And to say that the velocity is in this direction, because I and j are completely independent, this is j direction, right? Then to say that the velocity is completely in the I direction is the same thing as saying that there is zero movement in the j. So that means that in my v vector, which would have an x component and a y component like all vectors in 2 dimensions, the component for j, i.e. this guy, the y component, has to be 0. That's what they're telling us. So we can use that clue to find out the value of t at that point where this is happening. So how does that translate into math? Let's write the general vector v as x and y, and then that's equal to our original position vector, original speed vector, because here we're talking about speeds, which is this guy. They tell us that that's at t equals 0, that's the velocity. Do we write that as a column vector? Is 5 minus 3, plus the acceleration vector, which they give us up there, is minus 3 plus 1 times the time. And they're asking us for a particular moment in time where the velocity only has an x component, so that it would be in this direction, and that only happens when this guy is 0 So our equation is the second one that we can extract the information from. We know that y is equal to minus 3 plus 1 times t, and y is 0 for velocity in I direction. Therefore, we know that 0 is equal to minus 3 plus t, so this implies that t is plus 3. So that's 3 seconds. We need to put it in seconds or just an s, because they tell us in the question, and this is something to notice, that this is in seconds. Sometimes t can be in hours, like the question we did recently with boats in the ocean. Okay. So that was for part A. Part B says to find the speed of the particle when time is 5, and we have here the general formula for the particle, and they're asking us for the answer for x and y coordinates of the velocity v, more than coordinates, just components, sorry, of the velocity v at time t equals 5. So that's easy, it's just subbing in a 5 into here and seeing what we get to for x. So here I have 5 minus 3 like over there, and then the velocity component, which is the minus 3 and 1, and time I've introduced here a 5, and I put it ahead because I'm going to multiply out and it looks a little bit more reasonable like that, instead of putting the 5 behind here, like over there. So what do I get? Well, 5 minus 15 is minus 10, and minus 3 plus 5 goes to positive 2. So that's now my vector for the velocity at time t equals 5. But notice that the question says speed, it doesn't say velocity. So they're actually asking for the magnitude of this vector. They're interested in, since speed is a scalar. So, how do you calculate the magnitude of a vector? Well, like in the last video, we take the square of each component and we square root the whole thing using Pythagoras theorem, and it comes out to be, I did a bit of algebra here, reducing roots and leaving it in an exact answer, and then I did it in a calculator also. But it's good to be able to go from long roots like that to like smaller roots if possible, because in all C1 and C2 and C3 and these exams in maths, you've got to be able to do that exercise anyway. So whenever I get a chance, I try to practice with reducing these things. Okay, so hopefully that makes sense. I had already done this and the recording came out strange, so I'm just doing the voiceover again because I didn't want to rewrite it all again. Basically, this with part B was quite easy, so that was okay. And we had that the velocity vector at t is equal to 5 was then minus 10, 2. Okay, the third part of the question, which I have up here and I also did and somehow repeating, said that we had to find the angle between vector I, which points in this direction, right, and velocity vector at t is equal to 5. And we just said that we found out that at t is equal to 5, velocity vectors minus 10 and 2, so these are the two vectors that we're interested in. I'm trying to find the angle between them. So when solving this, I drew in a diagram vector I to the right, making sure that it was clear that I is going to the right, and I drew vector minus 10, 2, which has a very long x component in the negative direction and a 2 in that way. So then I got an idea for what the vector looked like, and therefore I have a sense for the angle that I'm interested in. And the angle I'm interested in is this theta, because it's the angle between positive I, right here, that does matter with vectors, the direction, and the vector that I just found for the velocity at t equals 5. Right? So I just used trigonometry to find this guy, theta dash, which came out to be the tan, and then I did 180 minus that angle to find my answer here, 168.7, which came out to be correct. And hopefully that process makes sense to you. Okay, I'll jump on to the next video now so we can cover some more stuff, and hopefully that, even though I didn't do it real time with you, has made sense. Alright, see you in the next one.